Okay, fine. So let's start. I'm happy to see everybody here for this seminar, and very pleased to have Andrew Marks at UCLA, and his title is there. I hope you can see on the shared screen. It's the Decomposability Conjecture. So Andrew.
Great. Thanks very much for the invitation. I'm going to talk about some joint work with Adam Day, who's in New Zealand. And it's about the decomposability conjecture in descriptive set theory. The rough outline of the talk is that we show the decomposability conjecture is true, assuming pi12 determinacy. The conjecture, the decomposability conjecture, is a pretty simple conjecture about what Borel functions are piecewise continuous. To me, it's still a very interesting open problem to try and remove the determinacy assumption here. There's no way you should need pi12 determinacy to prove something this simple about Borel functions, but we use it at the end to cheat and not do enough hard work. The other interesting aspect of this is that the heart of our proof is a new characterization of when a Borel set is sigma 0 n complete in the Braille hierarchy. And that characterization is proved using priority arguments. But priority arguments usually are a technique that you see in computability theory. Here we're using them in descriptive set theory. And in particular, we're adapting a new kind of framework due to Antonio Montalban called the true stages framework for organizing and making priority arguments work easily. But it's turned out people in the last couple of years have realized that something very much like Antonio's true stages machinery has, in a hidden form, been around in descriptive set theory for a while. When Louveau and Saint-Ramond proved Borel wage determinacy in second order arithmetic, essentially they used something very much like a priority argument and used something very much like the true stages machinery. So I want to talk about this a bunch as well. Okay, so now that I've spoiled everything in the talk, and let's start. Okay, so as usual in descriptive set theory, we were going to be working with Polish spaces. So Polish spaces are completely metrizable, separable topological spaces. And if you like, for the talk, you can just think about, the usual set theorist version of the real numbers. Take the power set of the naturals, 2 to the omega. But there's many other natural Polish spaces that come up in descriptive set theory. And let's recall the Braille hierarchy, which measures the complexity of subsets of a Polish space. And it's a transfinite hierarchy defined the following way. The sigma 0, 1 sets are the open sets. And the pi 0 alpha sets are the complements of the sigma 0 alpha sets. And then in general, a set is sigma 0 alpha if it can be expressed as a countable union of pi 0 beta sets for betas less than alpha. Okay, so maybe I'll draw a picture here quickly. You have the open sets, and here the complements of open sets are closed sets, and the intersection, right, would be the clopen sets, though I haven't defined the delta classes. I guess A is delta 0 alpha if A is both sigma 0 alpha and pi 0 alpha. Okay, so here's delta 0, 1, the clopen sets. And then sigma 0, 2 sets obviously include both pi 0, 1 sets and sigma 0, 1 sets. And this continues into the transfinite. Okay, so like a countable union of closed sets, for example, is sigma 0, 2. There's a standard way of comparing the complexity of Borel sets, and that's wage reducibility. We say A is wage reducible to B if there's a continuous function f, so that for all points x, you have that x is in A if and only if its image under this continuous map f of x is in B. And note, by the way, that since f is continuous, if B was open, the preimage of B under f is exactly A here, if this is the case. And so A would also be open. And transfinitely, that works through the Braille hierarchy. If B was closed, A would be closed. If B is, say, sigma 0, 2, each of the closed sets whose union is B would have closed sets in it as preimages, and so their union would be A, which would also be sigma 0, 2. So if A is wage reducible to B, then it's the lower level of the Borel hierarchy. If B is sigma 0 alpha, then A is also sigma 0 alpha. Okay, and a couple of last definitions. A set is sigma 0 alpha hard if every sigma 0 alpha set is wage reducible to it. Okay, and a set is sigma 0 alpha complete if it's both sigma 0 alpha and sigma 0 alpha hard. So complete sets are important in the Braille hierarchy because, well, one reason is that they're the way we prove the Braille hierarchy is proper. In this picture that I drew before, it's easy to check that there is a closed set that's not open and an open set that's not closed. And then transfinitely, there's a sigma 0 alpha set that's not sigma pi 0 alpha and so on. And the way we prove this is with a straightforward diagonalization argument. We make what's called a universal set whose sections give you every possible sigma 0 alpha set. And then we can use that to diagonalize and show that if a set is sigma 0 alpha complete, if it's as complicated as any other sigma 0 alpha set, then it's not pi 0 alpha. Okay, so the Braille hierarchy is proper. Okay, so that's a quick review. I hope most people here are familiar with the Braille hierarchy. Let's move on to the decomposability conjecture. And the decomposability conjecture is trying to characterize what functions are piecewise continuous. Okay, so by piecewise continuous, I just mean a union of countably many partial continuous functions. So sometimes you'll see this called a little bit more precisely sigma continuous, indicating the union here is countable. But for Borel functions, that's the interesting notion. Okay. So can we characterize piecewise continuity? Let's step back for a second. Imagine our function is between metric spaces. One definition of continuity is the epsilon delta definition, right? But there's this more syntactic characterization of continuity that uses the Borel hierarchy. A function's continuous if and only if the epsilon delta definition, but also if the preimage of every open set is open, right? Okay, so is there an analogous kind of characterization of piecewise continuity? Can you say something like you're piecewise continuous if and only if the preimages of these kinds of Borel sets or these kinds of Borel sets? And that's what the decomposability conjecture tries to do. So here's a very easy observation. Suppose you have some function and it's f, it's between two Polish spaces, and you can write it as a union of countably many partial continuous functions. But each of those partial continuous functions has a domain with this complexity in the Borel hierarchy. It's delta 0n. Okay. So here's a quick calculation. If you can write your function as a union of piecewise continuous functions with these kinds of domains, then if you have a sigma 0n set, the preimage of that sigma 0n set under a continuous function, this f sub I, is still sigma 0n. But that it's sigma 0n in the relative topology in the domain here of f sub I. But since this domain is delta 0n, this preimage is the intersection of a sigma 0n set with the delta 0n set. And so it's still sigma 0n. Okay. So the preimage of the whole set A is the union of the preimages of each of these individual pieces. And so it's a countable union of sigma 0 n sets, but that's still sigma 0 n. Okay, so if you have a function and it's piecewise continuous, and each of the pieces have domains that are delta 0 n, then you have the property that the preimages of sigma 0 n sets are sigma 0 n. And in the 2000s, various people turned this into a conjecture. That is the converse true, basically. Suppose you have some f. Is it the case that it's a countable union of continuous functions with delta 0 n domains if and only if the preimage of every sigma 0 n set is sigma 0 n? Okay, so as we said, this very trivial argument here shows that the forward direction of the conjecture is true. What's difficult is the reverse direction. All right, so there's a more general conjecture, which isn't going to be that important to our talk, but a function is a countable union of Baire class M functions now with delta 0 n domains, if and only if the preimage of every sigma 0 n minus m plus 1 set is sigma 0 n. So a little more generally, if you care about the property of being piecewise Baire class M, and recall, by the way, that this is the standard way of measuring complexity for functions in the Braille hierarchy. You measure the complexity of sets with the Braille hierarchy. You measure the complexity of functions with the Baire class hierarchy. Baire class 0 functions are the continuous functions. And then you say a function is Baire class alpha if it's the pointwise limit of a sequence of functions of Baire class less than alpha. Okay, so a Baire class 1 function is a limit of continuous functions, pointwise. And then a Baire class 2 function is a limit of Baire class 1 functions, pointwise. And there's a more syntactic way of talking about being Baire class alpha. Your Baire class alpha, if and only if the preimage of every open set is sigma 0 alpha plus 1. Okay, so sigma 0 alpha plus 1 measurable, if you like. Okay, so this generalizes this conjecture about piecewise continuity here. And what Adam and I do is we prove this conjecture, assuming this determinacy hypothesis, which I would very much like to get rid of. But that's an open problem. Okay. So there was some prior progress on the decomposability conjecture. Jane and Rogers were motivated by some problems in Banach space theory, and they proved the decomposability conjecture is true for n equals 2. So f is from x to y is piecewise continuous. With delta 0 n domains, if and only if the preimage of every sigma 0 2 set is sigma 0 2. Okay. By the way, because a delta 0 2 set is sigma 0 2, that's a countable union of pi 0 1 sets, right? And so you can break up this continuous function into each of those pi 0 1 sets and instead say f is piecewise continuous. It can be expressed as a countable union of functions with pi 0 1 domains. And this is often what we mean by piecewise continuous, like an analysis. We can break the function up into closed sets on which it's continuous. Okay, these sets, though, by the way, these domains, if you make it pi 0 1, aren't necessarily disjoint anymore. You can't write an arbitrary delta 0 2 set as a union of disjoint pi 0 1 sets. So if you have delta 0 2 here, the domains are all disjoint from each other. If you have pi 0 1, they may overlap. Okay, so Jane and Rogers proved the conjecture for n equals 2. In much more recent work, coming basically from Brian Semis's PhD thesis and then built on a little bit by Dean Kihara, Semis, and Zhao, the decomposability conjecture is true for n equals 3. Okay. And The theorems are proved the following way. Remember, the conjecture says you're piecewise continuous on delta 0 n domains if and only if the preimage of every sigma 0 n set is sigma 0 n. So we want to prove the left implication, but instead we do the contrapositive. So to prove the contrapositive, you show if your function is not a union of functions with these domains, then you can make a sigma 0 n set whose preimage is not sigma 0 n. And how do you show something is not sigma 0 n in the Braille hierarchy? Well, you show you can reduce a complete pi 0 n set to it. You show that it's pi 0 n hard. Okay. So this is getting towards this, this main machine in our proof. We have a new way of proving that sets in the Borel hierarchy are hard at some level in the Borel hierarchy. Okay. And we want that kind of machine because the central problem in proving the decomposability conjecture is constructing one of these sets whose preimage is not sigma 0 n, but you prove that by showing that you can reduce some complete pi 0 n set to it. Okay, so proving these kinds of hardness results in the Braille hierarchy is not straightforward. In fact, if you look in Kekris's classical descriptive set theory book, at some point he says it's an open problem to come up with any natural sigma 0.5 complete set in the Borel hierarchy. It's not something that people do very often. It's hard to prove those kinds of theorems, but Adam and I, stealing ideas from computability theory, prove a theorem that says you're pi 0 n hard if and only if, and then some characterization that's useful for proving this. And it uses ideas coming from priority arguments in computability theory. So I'm going to talk about that for a while now. But maybe I should stop and ask, are there any questions before we go on? We're going to move out of descriptive set theory for a second. Okay. So what are priority arguments? They're a tool used in computability theory in general to construct simple kinds of objects. A very typical example of something you make with a priority argument is a computably enumerable set. So the set itself has a very simple definition. This is a sigma 0.1 subset of the natural numbers. But you want to control complicated properties of this RE set that you're building, of the CE set that you're building. Like what kind of Turing degrees are below it, for example. So the term priority here comes from the fact that when you're building this set, usually there's a bunch of different properties you want it to satisfy. There's different this is the technical term here, requirements that this CE set, or in more generally, this object you're building needs to satisfy. And sometimes they conflict with each other, these different requirements that you're trying to satisfy. And so what happens is that these priority arguments give each requirement here that you're trying to make hold a priority, and when they're conflicting, the higher priority argument is given preference, and the lower priority argument is, and this is the technical term again, is injured. And you kind of delicately arrange the construction so that you can prove by induction that all the requirements are satisfied. The very easiest kind of arguments like this arrange the priorities in some well order, and you say that the highest priority argument eventually gets satisfied. And once that requirement is satisfied, then the next highest priority requirement will eventually get satisfied and be injured only finitely many times. And then inductively, each requirement only gets injured finitely many times and will eventually be satisfied. Okay. These kinds of proofs began with the work of Friedberg and Muchnik in the 1950s. Friedberg being in the US in Muchnik in the Soviet Union, and so there was this time where there wasn't much communication between these mathematical communities, but essentially the same idea got invented independently by these two mathematicians. The precise mathematical problem they were trying to solve was what's called post problem in computability theory. So there are two RE sets which can't compute each other. And well, I guess a little more generally show that there is an RE set that can't compute the halting problem, but isn't computable. And the way they showed it was by making two incomparable RE sets in the Turing degrees. Friedberg and Muchnik were undergraduates, but they solved this problem, which had been open for almost a decade in computability theory and was regarded as very important. And I like to think the reason was that they conceptualized computation in a different way than many other researchers. The computer programs that you kind of need to write to do this kind of enumeration are very complicated. And there's infinitely many things going on at one time, and you need to mediate conflicts in between them. And so if you try and do something like write down in lambda calculus or use, partial recursive functions like Herber and Gödel, you just can't write down easy definitions of these kinds of CE sets. What you need to do is informally describe some algorithmic process for making them, and then appeal to the Church-Turing thesis. And so by thinking of algorithm in this more kind of informal way, it becomes possible to make these kinds of complicated programs. Okay, and as time went on, programs that you make via priority arguments in computability theory got more and more complicated. The 70s and 80s especially were a time when some of these algorithms for making these CE sets run to many tens of pages, and you're very informally in this long mathematical paper describing one incredibly long and complicated computer program. And they got very difficult to digest and understand. And in reaction to this kind of problem, people proposed making some frameworks for modularizing these kinds of priority arguments. Okay, sort of like in around the same time in computer science, people found that maintaining and creating very long computer programs got incredibly messy and complicated, and some sort of engineering kind of mindset was suggested to try and systematize and make easier to understand and maintain these kinds of programs in real life. And that was the field of software engineering. Okay, so by the time like I was doing my PhD in computability theory in the 2000s, there was something of a backlash to these kinds of frameworks for priority arguments. Similarly, by the way, to how there was a bit of a backlash against software engineering around a similar time. I'm putting a pretty famous quote of the famous computer scientist Dijkstra, who really didn't like the field of software engineering. He thought that the ever increasing complexity of computer programs could never be kind of systematized and made easy to work with in the way that software engineering wanted. And he said that the whole idea of the field was self-defeating. So by the time of the 2000s, maybe, this is, I think, how most computability theorists regarded these kinds of priority argument frameworks. In fact, a famous framework of a couple computability theorists I was talking with a few years ago, and they, with one of the authors, and they completely disavow the entire large book that they wrote about it. They say it's not a good thing to study or use anymore, and that it was a little, in retrospect, misguided approach to the problem. Okay, so I think, though, that despite all this, and this was kind of received wisdom then in the 2000s, that these kind of frameworks aren't the solution, there's been a change of heart in computability theory because of work of Chris Ash and Antonio Montalban. So maybe framework isn't the right terminology for Montalban's true stages machinery, but Montalban created around 2014 a technique for organizing priority arguments, which he calls the method of true stages. And it's starting to be used a lot in computability theory, especially in computable structure theory. It builds on earlier work of Chris Ash. Chris Ash was inspired a little bit, incidentally, by the proof of Borel determinacy. So it has some roots in descriptive set theory, Ash's framework, which Montalban builds on. But it's now that we're understanding true stages better, one of the reasons I think you can say that it's really important and natural, unlike maybe prior attempts at systematizing priority arguments, is that it's arisen independently outside of computability theory, where priority arguments are almost always found. So Day, Greenberg, and Turetsky were looking at Louveau and Saint-Mamon's proof of Borel wage determinacy in second-order arithmetic. What is this theorem? If you take the wage order on Borel sets that we defined earlier, you can prove using analytic determinacy quite easily, or I guess Borel determinacy, that the wage order is a well quasi-order. There's no infinite descending sequences, there's no infinite anti-chains. Okay, but Borel determinacy uses a huge amount of ZFC to prove, right? And it was an open question for a long time whether this pretty fundamental and basic fact about Borel sets could be proved in any simpler way. And the answer is, in fact, yes, that you can prove wage determinacy for Borel sets, the fact that the wage degrees are well quasi-order just in second-order arithmetic. But Louveau and Saint-Mamon's proof basically now from a computability theoretic perspective is almost exactly the true stages machine. And Louveau and Saint-Mamon created their version of true stages to deeply understand how you witness membership in a sigma 0 M set. And that's precisely what's going on in Montalban's true stages machinery. And so now I think this is an important and very natural thing to understand and investigate a little bit further. Okay, so in our work, we use priority arguments kind of the same way that computability theorists do. You remember I started off by saying you use priority arguments to make a simple object that has some sort of complicated property. And we're still doing that. We make a simple object, and for us, it's a continuous function. But it has some complicated property, and the complicated property that we want to satisfy is that it's a wage reduction between two quite complicated Borel sets, a complete sigma 0 n set and some other set. Okay, in trying to make this continuous function behave well on this sigma 0 n set is difficult, and in doing so, you need to sort of understand during the construction how you end up inside that sigma 0 n set or not, what a witness to that looks like if you start unraveling it. Okay. So I want to give you a complete proof of a very simple level of our theorem. So in a second, I'm going to say that a set Y in the Braille hierarchy is sigma 0 n plus 2 hard. So there's a continuous reduction of a complete sigma 0 n plus 2 set to it if and only if, and then a couple conditions. Okay, and then you prove this characterization of sigma 0 n plus 2 hardness using one of these true stages arguments, one of these priority arguments. Okay, but I'm going to prove a very simple version of that theorem and give the complete proof. And you'll see, if you've seen priority arguments before, how they naturally show up here. Okay, so I need a couple more definitions before I go on, and we're going to be proving the sigma 03 completeness level of our characterization. So I need some terminology from Bare category. So a set is meager if it's contained in a countable union of nowhere dense sets. Okay, this is, of course, the standard topological way of measuring largeness, right? You would like to say that a set is large if it's dense, maybe, and small if it's nowhere dense. But those notions aren't closed under countable unions and intersections the way you would like ideals and filters, which measure largeness notions, to be. And so you fix them. You force them to have those countable unions of small sets are still small in this sense by allowing countable unions in your definition. A set is meager, so this is like topologically small if it's contained in a countable union of nowhere dense sets, and co-meager if its complement is meager, okay, which by definition means there's countably many open dense sets whose intersection is contained inside B. Okay, so this is just a definition for the purpose of our theorem, but you say a collection of countably many closed sets is good if it's closed under finite intersections. And for any basic open set, if the intersection of your closed set with that basic open set is not empty, then there's another closed set that sits completely inside it. Okay, so the closed sets you're going to be using in a minute as approximations to where the image of a point goes under a continuous function. And one of the commitments that you make while you're making a continuous function is you say, I'm going to send this open set to this open set. And we want the closed sets to be able to be sort of pruned and refined along with those kinds of basic open approximations. Right. So an example of a good collection of closed sets would be all the light face pi01 sets in Cantor space, for example. Okay, so here's, I've never seen this written down anywhere in the literature, but every single time somebody proves a set is sigma 03 complete in the Braille hierarchy, and there's a lot of theorems like that, they're basically doing this. And they have to be doing this because this is an if and only if theorem. A set is sigma 03 hard, that is a complete sigma 03 set reduces to it, if and only if there's a good collection of closed sets. So countably many closed sets with these simple intersection properties and refinement properties. You can refine one of these, the elements of your collection, to be inside any open set. So that if you're an element of infinitely many of these closed sets, then you're not an A. And A is large in each of the closed sets in the sense that it's co-meager in them. Okay. So once you have this theorem, by the way, a lot of results, like, I don't know, they're like recent results, say, of Ted Slayman and Veronica Bescher, that the set of normal numbers to some base, for example, is sigma 03 complete. They become quite a lot easier because you remove the priority argument out of the theorem and it becomes just a quest to find these closed sets. And often in practice, the closed sets are quite natural. Like in the example that I just mentioned, they're natural fractals in Cantor space. And then checking that this bare category condition is true is pretty straightforward. And checking this condition is also pretty straightforward. You construct these closed sets basically so that once you're in infinitely many of them, you know you're not going to be inside A. Okay. So I think in practice, a lot of times people have reproved this theorem in the middle of their sigma 03 completeness result, but you don't need to. You can just do it once if you want. And similarly, you can just prove this theorem we have characterizing sigma 0n hardness once, and then check these pretty easy kinds of topological conditions to check that you have the right kind of approximations to making one of these continuous maps. Okay, So there's two directions to prove here. You need to show that if there are these good closed sets and they have these two properties, then A has to be sigma 0, 3 hard. Right? And that's the more difficult direction. So it's a finite injury priority argument. And I'm using notation here from computability theory, so sorry about that. But fix a bijection, I'm going to use these angle brackets to indicate it between omega squared and omega. And here, basically, I'm viewing an element using this bijection of x is really an element of 2 to the omega cross omega. Okay. So let's think about the set of points x so that there is some I, so that there are infinitely many j, so that x at the ijth coordinate is a 1. Okay. So if you like, this is the set of points so that some section of x is infinite. All right, and this is an easy and canonical example of a complete sigma 0, 3 set in the Borel hierarchy. Exists infinitely many is the same thing as saying for all n, there exists some x greater than n, right? So we're contracting two quantifiers into one by using that. So that's why this is sigma 0, 3. Okay, so once you check that C is sigma 0, 3 complete, which is a standard fact, it suffices to show there's a continuous reduction from C to A. And that'll show that since any sigma 0, 3 set reduces to C, by composing the reduction from C to A, it also reduces to A. Okay, so inside each of these closed sets, F sub n, you know that A is comeager. And so you can find countably many open dense sets so that after you take the intersection of them, that's contained inside A. All right, and so now we make our continuous function. So you have a Cantor space here, 2 to the omega, and you want to make a map from it that's continuous to this other space X. And what we'll do is at each point in time, we'll have an approximation for where this continuous function goes. So for each finite string S, we'll say that f of x is approximated, f of x for x extending S is approximated by the following data above. So it's going to be approximated by this basic open set rho of S. So we're going to say that extensions of this finite binary sequence go inside this basic open set, rho of S. And then there's going to be a little bit more data we're tracking. So we'll also have a a finite collection of decreasing closed sets that meet our basic open approximation. Okay. And so what happens is that at each point in time, you think about finite strings that are longer and longer. And if you start seeing more and more zeros in these finite strings, you think, maybe we're not seeing more ones. Maybe all the columns here are finite, and so we should be outside of A. And so in that case, you extend the collection of closed sets that you have. And you know eventually, if you end up being in infinitely many of them, you're going to be outside of A. That's this condition here. So as you see more and more zeros, you keep building this collection of closed sets. And if you're in all countably many of them, you end up outside A. And each time you see a 1, then you injure this kind of list of closed sets that you imagine that you're in. And you meet the next dense open set in the ith closed set, where I is the first coordinate of this new one that you saw. So here's a picture of an element of 2 to the omega cross omega. As time goes on, you start looking at more and more of the bits here. And each time that you see a 1, another 1 in some particular column here, there's a closed set attached to this column, and you meet another open dense set inside it. And so if there's infinitely many 1s here, you're going to meet all of these countably many dense open sets, and then you will end up inside A. Okay, and if inside each of these columns you only have finitely many 1s, eventually the closed set that you have here in this list will stabilize, won't get injured after finitely many points in time, and you will eventually be in all of these countably many closed sets. Okay, I'm teaching the basic computability theory class right now, and if you stare long enough at this proof, it's very reminiscent of the proof that if you take a uniformly CE collection of sets, the indices for those that contain some infinite CE set is sigma 0, 3 complete. That's a very simple example of a finite injury priority argument in computability theory. And this is just a sort of relativized version of that same argument. Okay, so that's the proof of this direction of the characterization. The other direction comes from 2 observations. The first is that inside this canonical complete set, there exist these closed sets F sub n for C. Right, and then once you have those closed sets witnessing that C is sigma 0, 3 complete, you can move them into any other sigma 0, 3 hard set by an observation of Harrington that if you have a weight reduction of some sigma 0, 3 complete set to any other set, you can make that weight reduction injective. And then once you have a continuous injective function, then the images of all these sets F sub n under it retain the same level in the Braille hierarchy and form the witnesses that you want. Okay, so let's talk about how this theorem is generalized throughout the Braille hierarchy. Here's some notation. If you have a countable collection of subsets of a space, let's let tau of A denote the topology generated by taking A as a subbasis. And the heart of the characterization that Adam and I come up with is comes from iteratively taking changes to topology on a space. There's a way to set up all of this using forcing if you prefer, but I think this is a little bit simpler. And descriptive set theorists are used to changes of topology, and so the first 3 change of topology conditions here are pretty standard. You see them often when you want to make sure you have a new Polish topology, not just some topology, but one that's actually Polish. If you start with this topology and then build another one on top of it that contains all the old sets, but now contains complements of old basic open sets, but just consists more generally of all closed, or a collection of closed sets, which is countable, then this will always be a Polish topology. And so you start with your basic open sets here, and now this is a collection of closed sets, but with some simple properties that make sure this is still a Polish topology. And now A sub 2 will be a collection of pi 0, 2 sets. But since you satisfy these basic closure conditions, it will still be a Polish topology on the space and so on. But this last condition is the hard one. This condition says that if you take a set at the m+1 level, so this is going to be a pi 0 m+1 set, and you take its closure in the a topology that comes from taking your pi0 m-1 sets, then it is one of the sets in your collection of pi0 m sets. Okay, you can't even, if you start with some finite list A0 up through AN of pi01 sets, pi02 sets, up to pi0n sets, and you try and close everything off to make condition 4 satisfied, there's no reason you should ever catch your tail. This says you need to enlarge a collection of pi0 m sets if your collection of pi0 m+1 sets contains some interesting b's. But once you enlarge a collection of pi0 m sets, then because of these conditions, your collection of pi0 m+1 sets should get larger again. And even after trying to close things off after countably many steps, condition 4 won't obviously be satisfied at all. Okay. One example, by the way, of sets that do have these nice properties is if you take the light face pi0 m sets to be the mth level in your collection. Okay, so that was something about what the suitable sequences are. They're collections of basic sets and then pi01 sets, pi02 sets, up to pi0n sets. And what's going to happen is that we're going to approximate a continuous function by elements in these collections where we say at each point in this construction, you have a basic open set approximating where you go, and then also pi01 set and a pi02 set and so on, all the way up to a pi0n set. This is all an approximation of what the image of this point is going to be under this continuous function. And the theorem says that you are pi0n+2 hard if and only if there's one of these sequences of change of topology so that your set here is meager in the top topology and co-meager in each level of the topology one level down. Okay, so the idea is that these are pretty simple bare category conditions to check. The construction to show that once you have these things, your set is pi0n+2 is hard is difficult. It's a hard priority argument. Okay, and it uses this machine of Antonio Montalban for approximating how you witness membership in some sigma 0 n set. Okay, maybe it's not worth going through this slide right now in detail. But this is the idea. Just like when you're proving a set is sigma 0 3 complete, at each point in time, you approximate this continuous function you're building by both a basic open set, but also a closed set. And the closed set that you're using for your approximation can change as time goes on and get injured. Now you have a longer sequence of a pi01 set, a pi02 set, all the way up to a pi0n set. Again, you use all of them during the approximation, and the flow of that construction comes from this machinery for understanding in a very detailed way how membership in a pi0n set is witnessed. So this is sort of the descriptive set theoretic version of Montalban's machine. Instead of working with subsets of the natural numbers, here we work with finite binary strings instead, so we get something that works nicely across all of Cantor space. Okay, so that's something about this characterization of sigma 0 n+2 hardness. Let me say now something about how you use that to prove the decomposability conjecture. Okay, and recall, here's the basic problem. You assume you have some function that's not a union of bare class M functions with pi0 n domains. You need to show that there is some set at the right level of complexity whose preimage is not what it should be. It's not sigma 0 n, and you show that it's not sigma 0 n by showing that it's pi0 n hard. Okay, but now using the machine I just talked about, we have a new way of understanding pi0 n hardness, or equivalently sigma 0 n hardness. Okay, so let me make a very easy observation about how changes to topology work. Suppose we have a topology x tau on some Polish space x, but we have a new topology, a new Polish topology, where we make countably many pi0 n sets in X tau the new basic open sets in X eta. So this is supposed to stand for new. Okay, so here's some really trivial calculations. If you have a sigma 0, 1 set, then it's a countable union of basic open sets, right? But the basic open sets I just said come from pi 0 n sets in the old topology. So a countable union of pi 0 n sets in the old topology is sigma 0 n plus 1. Sound good? So this is something we use all the time when we're changing topology. The new open sets are old pi 0 n plus 1 sets if we do this process. Okay, a similar argument shows you any sigma 0 k set in the new topology comes from a sigma 0 n plus k set in the old topology. Okay, and let me take the contrapositive of that statement. If you're not sigma 0 n plus k in the old topology, then you're not sigma 0 k in the new topology. This is just the contrapositive of that. Okay. So the converses here are extremely false. Okay. Suppose you have a arbitrary sigma 0 n plus 1 set here. It's a union of countably many pi 0 n sets, right? But not necessarily the countably many pi 0 n sets you use to change topology. So there's no reason it should be sigma 0, 1 in the new topology. Similarly, it's not the case that if you're not sigma 0 n plus k in the old topology, then you're not sigma 0 k in the new topology. Okay, so hoping for something like this is just silly, but that's what we do. All right, here is our naive attempt at proving decomposability. We take a function which is not a union of Baire class n-1 functions with pi 0 n domains. We change the topology by making some pi 0 n-2 sets the new basic open sets. And then by using this observation, it's easy to see that our function now in this new topology is not a union of Baire class 1 functions with delta 0, 3 domains. Okay, so we can apply the existing case we know of the decomposability conjecture. The decomposability conjecture has already been proved for n equals 3. And so after we change topology like this, we obtain a sigma 0, 2 set whose inverse image is not sigma 0, 3. Okay, and now we could hope that this set, which is not sigma 0, 3 in the new topology, is not sigma 0 n in the original topology. And if that happened to be true, we'd be done proving this case of the decomposability conjecture. Okay, but as we just discussed, you can hope that this is true, but it's not in general. It's horribly false. Okay, you can't ever, nobody ever proves theorems in descriptive set theory this way, by induction on the Braille hierarchy, by changing topology, and then hoping ridiculously like this that things work how they would in the best possible case. Okay, but what we do this is try and do this a lot. Okay, we keep doing it over and over again and hoping each time that it works. And what we prove is that eventually, after countably many steps, we do make that silly idea to try and prove the theorem work. And it goes as follows. Each time this idea we had fails, we get a new pi 0 n-2 set, one of the sets that make up the definition of this set here that we have, to add to a collection of sets that characterizes sigma 0 n hardness. Okay, using our characterization from before of when a set is sigma 0 n hard. So each time this idea that I had fails, we get another set to add to our collection to try and show that this set is sigma 0 n hard, a set to add to our changes of topology. Okay, and this isn't for free. It requires a careful analysis of how the n equals 3 case of the decomposability conjecture works. But once you establish that, we eventually succeed at some countable ordinal stage because of the following theorem of Leo Harrington, assuming AD, there's no Aleph-1 length sequence of distinct Borel sets of bounded rank. So if we kept doing this and we failed every single time for omega-1 many steps, we would get a sequence of distinct pi0 n minus 2 sets. And that would be a contradiction. So eventually that collection of sets we use to change topology has to become closed off, and then we prove that the set that we want is complete. You might know a special case of this theorem, right? Assuming AD, there's no omega-1 sequence of distinct reals. But it was a big project in the 70s to figure out the longest sequence of distinct this, that, or the other. And one of the items that people analyzed was elements or collections of distinct Borel sets. And this is the bound there. And if you work through Leo's proof carefully, for what we need, we can get away with just pi12 determinacy. Okay, so this way, by the way, of proving the theorem is cheating, we have this characterization of when a set is sigma 0 n hard, we should just use it in one step to prove the theorem and use the kind of standard techniques people know using reflection and forcing to define from the outset the correct sequence of sets needed to witness that our set is pi0 n hard, but we haven't been able to make that work, so that's still open. Okay, I'll stop there. Thanks very much.
Fine. Thanks very much, Andrew. It's really interesting. So, any questions from people?
I have a completely tangential question about Borel wage determinacy. So you described it as saying that the wage ordering on Borel sets is well quasi-ordered. If I remember correctly, Borel determinacy is also used in showing that the wage ordering on Borel sets is almost linear up to dualization. And those two proofs, at least the proofs that I've seen, are sort of disjoint from each other. And the linearity business is much easier. Is there any direct connection between those two applications of Borel determinacy to wage, or is it just that they both happen to be consequences of full-scale Borel determinacy?
That's a good question. I'm not probably the right person to answer it, but I do know that as part of Louveau and Saint-Ramon's careful analysis of the Borel wage degrees in second-order arithmetic, they get the almost linearity as part of their analysis. So you don't need full Borel determinacy to prove that theorem. But I don't know of a good abstract connection between those two facts, other than going through either the detailed Louveau-Saint-Ramon analysis, which analyzes in excruciating detail every single Borel set in order to figure out exactly how it fits inside the Borel wage degrees, or the two proofs that you mentioned that are more abstract from Borel determinacy.
I have a question. So, okay, so you're using this determinacy as a critical component of the proof, and I'm wondering, because of course a priority argument, I mean, media requirements and so on, is something like playing a game. And so is there any way of sort of using the determinacy more fully by presenting the whole construction as a game of some kind and then using the strategy from that game to make your conclusion? Or are you happy to have isolated off the consequence of AD about the omega-1 sequence of Borel sets? I mean, how?
So when Louveau and Saint-Ramon made what they consider or what is equivalent to the true stages machine, they did it in terms of games, right? The French school of descriptive set theory loves game style presentations and proofs, and it does really simplify some details of what they do. And so the true stages machine can definitely be formulated in terms of games and thought of that way very effectively. But if we did that, we would still, at the end of our proof, need to do a completely different determinacy argument to show that this process we have of building more and more Borel sets has to terminate at some countable stage, so that we can get the theorem that we want. And that, I think, would have to be completely separate. I don't know of any way of integrating the two things.
Thank you.
Can I ask a question?
Sure, Ramesh, go ahead.
Yeah. Hello, Philip. Yeah. First, an easy question: who are the two authors who have reneged on their book? If you may.
Oh, sure. I don't think they mind at all. The framework that I mentioned is due to Stefan Lemp and Manuel Lerman. And it was Stefan that I talked to about the book, and he thinks that it's not the right way of doing things.
Okay.
But you can go read the book if you like.
Okay.
It's a couple hundred pages, and it is something about a framework for priority arguments.
All right. Now, the other question is more mathematical. Now, the Harrington theorem you mentioned at the end, that's a nice, elegant theorem. It's the first time I see it applied anywhere. Perhaps I don't know much about other things, but do you know if other people have used it to prove something which has nothing to do with the?
Yeah, I've never heard of it being used. I didn't know the theorem. That it comes in the middle of Harrington's famous paper on zero sharp and sigma 1 determinacy, and he mentions this other beautiful theorem kind of as an aside in the middle, which isn't related to much else that he's doing in the paper. I didn't know the theorem, and so we realized that we had this transfinite procedure for making more and more Borel sets, and then we tried to prove on our own that eventually it has to terminate, and we couldn't, and eventually searched the literature and found Harrington's result.
So you don't know of another application?
I don't know of any other applications.
Okay, thank you. Thanks.
So you can't, if you're going to restrict this down, you talk about pi0 alpha sequences of sets. I mean, are there kind of simple low-down versions of the theorem where you can use less determinacy, or is it always just pi1,2 determinacy you're appealing to blankly? I mean, as your tool.
I don't know how to simplify it more than pi1,2 determinacy. I would love it if somebody got it down to analytic determinacy.
Right.
The Harrington doesn't do the localization of his argument down to the projective. For instance, there's no projective omega-1 sequence assuming projective determinacy, but he doesn't know that in his paper or prove it. And it's not completely simple to do that, because Harrington is forcing over L-like models to prove the theorem. It's not just an easy application of determinacy. It uses a lot more of the structure theorem, theory of AD.
Right.
So I would really like it if somebody did a better and more intricate calculation of exactly what you need to prove the theorem at various levels of the projective hierarchy.
Right. So at the moment, it doesn't help to put yourself inside, simpler models or something like that. I mean, L-like models don't help at the moment because you're still just appealing to this pi1,2 determinacy.
Yeah, so far as I can see right now.
Yeah. Oh yeah, that's interesting. Right. Any more questions from anyone?
Maybe I can make a historical comment, if I can remember the history correctly. Being old has the advantage that the history happened while I was watching, has a disadvantage that I may be misremembering it. But if I'm right, I believe that before Lemp and Lerman worked out their framework, there were at least two other framework attempts, both in the direction of making priority look more like forcing, one by Lachlan and one by Yates. And for all I know, there may have been others that I didn't hear about, but this seems to have been a fairly common idea that this really ought to work, but I don't know that any of the ideas actually turned out to really work.
Yeah, I'm not an expert on the history, but there's not just the one attempt. There were a bunch, and they were all motivated by what you said, to try and make things work in a more modular way, like forcing does. And I don't think any of the ones, from the 70s and 80s, when people were spending a lot of effort on this, are considered to have succeeded.
Yeah. Andrew, did you say a minute ago that you were hoping the determinacy hypothesis would be reduced for your theorem or for Harrington's theorem? Or I guess both.
For our theorem, it's such a simple fact of Borel functions, it shouldn't need any determinacy.
Right, but is it conceivable that the Harrington theorem could use this? Is there some reason?
I think maybe the optimal thing is that if you have an omega-1 sequence that's analytic, you should probably be able to get away with analytic determinacy. So that would improve our theorem too. We could assume, sigma 1 determinacy here, but I'm not the right person or expert to look at that.
No, I mean, that looks feasible, yes.
Yeah.
I have another kind of woolly comment. I mean, unless there are any more serious questions, my question isn't terribly serious. Does anybody else want to pitch in and ask anything?
Yeah, maybe I will.
Go ahead. Go ahead.
First, it's very nice to see you, Andrew. It's really good.
Yeah, good to see you too.
Good to see you. More mathematically, I guess it's a dream come true somehow for the descriptive set theories that this very naive attempt of changing the topology somehow works out after many steps, since it's somehow, I guess somehow you find the right change of topology so that the naive arguments work, right? Do you have any feeling about the fact that somehow this is the only way to go through some kind of priority argument, or is there like something about the problem of finding the right change of topology, the right sets to change, that makes this priority argument somehow the only way to go? Or is there hope that somehow we could describe this change of topology without going through the whole process of trying and adding the new elements?
So of course, Louvot's theorem that if you have a set that's light face delta 1 1 and bold face sigma 0 alpha, then it's light face sigma 0 alpha using some height parameter. So that is a beautiful theorem, and it uses some delicate reflection arguments. But if you look deep into the details, the collection of sigma 0 alpha sets that Louvot uses to do this kind of forcing argument to show that this is true, they satisfy exactly these conditions that I need about change of topology. They satisfy all 4 of these conditions. And so the original hope is to just by reflection show that any delta 1 1 set on which you're piecewise Baire class M with the right domains, you can find a maximal pi 1 set with that property and then take its complement and then work inside the remainder of the topologies you use from Louvot's argument and prove the theorem in one step without iteratively looking for more changes in topology. And we tried and we couldn't make that work. But I think that's the right way to do it roughly. But and that would remove all the determinacy. But more generally, your question is about, is this the right way to understand sigma zero n sets and to prove that they're sigma zero n hard or complete? I think emphatically so. The descriptive set theorists have been studying this question for a long time, like Halvouveau and Saint-Ramond, and then other people like Lecomte have done. And they've all come up with, in some form, basically this machine. And completely separately, with no communication between them, the computability theorists have been studying the same thing. And after a long time and hard work, they've settled roughly on the same machine. And I can't think of better evidence that this is the right way of doing things than two hard working groups of mathematicians studying the same class of problems, but no communication between them, coming up with exactly the same way of doing things.
Thank you. Yeah. So there's maybe hope to remove the determinacy hypothesis by like using that argument in a different way to somehow find the right change of topology at once, right?
Yeah,
maybe
that's the hope, I think. And somebody better than I am at those kinds of arguments should be able to do it, I hope. But I don't think at the end you'll be able to get away from these kinds of techniques for proving sets are complete in the Braille hierarchy. I think it's the right way to do it.
Yeah, there's historical evidence here, yeah, and hard work. Thanks.
Anything further? My ears only pricked up when you spoke about the kind of early history of Friedberg-Muchnick results and how this might have come about by a change of attitude. Other people have said, I suppose, I mean, more as a kind of critique of the Kleinian school, that actually has kind of been stifling, in the 50s and 60s, this kind of extreme emphasis of, equational calculi and formalism that was based on that rather than the more, as it were, free-spirited Turing-based approach. So it was interesting that you also said something like that, Andrew. You can conceive of that as being quite true in many ways. So that was my woolly comment on what you said there.
I think, post-address and post-problem were pretty influential in computability theory, but it always was amazing to me that the problem, especially after the work of Kleinian and post, stayed open for 10 years almost.
Yes.
As an experiment, I have taught computability theory courses where, as a homework exercise, I assign the Friedberg-Muchnick theorem after I've done Kleinian post, and I don't tell them any terminology or things that they could use to, look up the argument somewhere. They have to really come up with it on their own. But they have, many students, I have given all computability up to the 40s and then asked them to do that next leap to prove Friedberg-Muchnick. And many tens of them have. Their constructions are complicated and difficult to read, and they invent all sorts of weird terminology for what they're doing, but it comes down to the same idea. But I think the way that you think about computation is vital there. You have to be able to think in this kind of informal way and not using this kind of more rigid syntactic functional calculus kind of approach.
Sure, yeah. No, it's interesting to muse about what Turing would have made of it, but I mean, he seemed to have kind of stopped doing those kinds of thinking about, he'd moved on. He was more interested in, morphology in animals and patterns and so on like this, rather than he kind of moved away from, computational theory. But it's just like something that he could have got his teeth into, stuck into, but didn't. Yeah. Okay, well, maybe we'll wind up unless anybody else has got something they want to add.
If I may speak of some work I did a long time ago, I did give a proof of Harrington's pi-on-1 determinacy in zero-sharp theorem using a different method without forcing and so on. I didn't look at all at the LF1 sequence of pi0 alpha sets and so on. Did you try to look at this in this particular way? No.
No, I'm familiar with your paper, which is very beautiful on zero sharp in analytic determinacy. But it didn't occur to me to look there for a different way of conceptualizing the proof. I think that's a good suggestion.
Okay, fine. Well, perhaps we can virtually thank Andrew. That was a great talk. That was really nice. Thank you very much.
Thanks.
So I'm silently clapping. Okay, so what do we do here, Joel? Usually we leave the link open and people can just make their goodbyes and leave when they wish or continue chatting if they wish. But...
Sure. Well, maybe we should announce that the next talk will be Peter Kolner in 2 weeks on March 10th. So please come back on March 10th. Hope to see everybody.